welcome to this session on inverse kinematics in industrial robots and manipulators. So I'm going to get us started. I have put together a number of examples, as Rochelle mentioned. Those are provided in the download link that has been shared with you in the chat. So it would be great if you guys can download and try to follow along. Before we begin, let's talk. I want to talk a little bit about the motivation behind this session. We've been working a lot with our customers on a variety of projects that would require some aspect of inverse kinematics, custom robotics, CNC machines, driving simulator, hydraulically actuated booms, like the ones that are mounted on a truck. These are the type of applications that we have been involved in, and our technologies are well suited for. So that gave us the inspiration to put together this session on inverse kinematics. This session will not be a complete treatment of the subject. This would be from our point of view and where our technologies and our approaches have practical use cases. So in particular, I will not be talking about iterative or Jacobian-based approaches. I'm going to, for the most part, stick to square systems. So the redundant systems will not be covered. There are some exceptions. And this session will not be touching on trajectory planning or optimization topics. What I will cover, as I mentioned, would be square systems, where we have the same number of actuated degrees of actuated joints and degrees of freedom for the end effector. We'll see examples of both open and closed kinematic chains. We'll have a special extension to the inverse kinematics for flexibility, and this is specifically for compensating the effect of gravity on the linkage, which could be a topic of concern for especially large manipulators. As we have covered in previous workshops in this series, we'll talk about cable robots as well. So let's very briefly talk about inverse kinematics. First, forward kinematics. In forward kinematics, we go from joint space to Cartesian space, where we have the value for the actuated joints, like this simple pictures. We have theta1 and theta2, and we want to find where the end effector is, or the x and y, which is usually a simple, straightforward problem to solve, and we plug in numbers to the equations and get the values. The inverse of that, which is the topic of this session, is much more complicated, involves many different numerical approach to get to the solutions. And there are sometimes no solutions, most cases multiple solutions that can come out of solving those nonlinear equations. So that's the premise. That's the area that we are going to be talking about. But as I mentioned, this is not a treatment of the topic. This is taken from applications that our technology has been tried and is been utilized. So let's have a look at the scope of what I'm going to be covering today. Just to put some context, we're talking about getting some equations, that these equations would be our what we want to solve to get to the inverse kinematics of the system, the robot, the manipulator. So then first is the derivation of where the equations come from, the process of solving them, and then putting them into a component, and then putting it in a bigger system model to simulate, or in a lot of cases, in controller automation, the next step would be not only simulation, would be to export so that this can be incorporated in the control code. So the one approach is explicit, is pretty straightforward, where we have the equations, we write them down ourselves, or we use Maple or a combination of MapleSim to get to those equations. We'll see how that would work, where we use just use Maple and its symbolic computation capabilities, or we use MapleSim to drive those equations for us and then give it to Maple for symbolic manipulation and attempt at solving. The solve obviously could be just manual, we have the solution, or we use Maple symbolic computation capability to do that for us. Then we will package that in a component. Usually there's a translation between Maple to Modelica. This could be explicit, where you have to tweak the code, and we'll see examples of that, or it could be done behind the scene by a command in Maple that will generate the component for us. Put it in MapleSim is another block, and we put it on canvas, connect it up, and we do the simulation. The one that is maybe not as direct as the first category is hybrid, and hybrid means that we don't solve everything. We might not be able to solve the equations, so we leave some of them unsolved and let the MapleSim engine deal with those nonlinear constraint equations. And this can continue to all the way to not solving any of the equations. So we just generate the equation, package them in a component, and pass it on to MapleSim for generation or export. And we'll see examples of that as well. And the easiest, most straightforward approach is just no equations at all, where we use the inverse of the model itself as our inverse kinematic. So that approach can be used in a variety of cases, and as I mentioned, it would be the fastest, easiest way to accomplish an inverse kinematic of a given system. And in some cases, this could be one of the few choices. Obviously, not all approaches are created equal in terms of reach and the type of system that they can cover, but also in terms of efficiency and how much work it is to get to them. So I put this qualitative graph together to give you an idea of these main approaches. So on the horizontal axis, we have the complexity of generation, as in how much work you need to do, the expertise level that you need to have to get to those solutions. And on the vertical axis, we have the computational efficiency. So the more work you do to get to the solved set of equations, then the overall computational efficiency would be higher. And that should not come as a surprise. Then we have the inverse models. There's in a lot of cases when we are in MapleSim and we want to use or create the inverse model, we can do some simplification to help us with, simplified in a lot of cases are better, and also provides some computational boost. So the simplification obviously varies depending on the case, and we'll see examples of how that would work and what type of simplification we're talking about. In terms of between implicit and explicit, also there is a range, and depends on how much of the equations you can divide and conquer and get to a solution for. The good news is that, as I said, not only simulation, but also the in automation control would be the users of these inverse kinematics solutions. And so there's usually a required performance in terms of efficiency of calculation and how fast they run. But the good news is, in many cases that we come across, even the inverse model would be way past the requirements. So we don't need to worry about that too much. Obviously, the more complicated the model becomes, the more computation power you need. and then other approaches could be make that difference. As I mentioned, there is a little bit of a special addition to the implicit approach that I hope that I get to as one of my examples, where we expand the implicit approach to creating an inverse kinematic block that also includes the compensation for the effect of gravity. For that, I'll convert a hydraulic actuator articulated boom to have one piece flexible and then drive the equations. Some of the topics that we are about to cover can be very technical. Hope that you still find the examples useful and give you an idea of how these technologies work. These are all created custom there's no universal solution aside from the inverse model that you just package the model and it has a wider coverage. When we get to equations, it is a case-by-case basis, but I hope that I would be able to give you the workflow from equations to inverse kinematics. So I'll be jumping from the presentation to MapleSim and Maple and back. So let's start with our first example. So a warm-up, a well-known robotic system, deltabot. For this one, we are going to use an explicit approach, and we'll just drive equations for the kinematic constraints in Maple, pretty straightforward for the deltabot, and then use Maple to solve those equations. Once we have the solution, we'll grab those equations, put them in a component using both Maple and MapleSim Modelica code editor, and then hook everything up as you see on the screen and simulate the system. So with that, I am going to jump to MapleSim. Here we go. So here's for those who haven't seen the product, the tool. Here's the modeling environment, and we have on the left our library of various components. And there's a message console on the bottom and the properties of components that we select on the right. And in the middle of the canvas is where the blocks are put together. So I'm just going to go and open the first example, which you also have in the package that has been shared with you in the download link. So just while I'm talking about that, I'm going to run this as well. So we have various blocks on the screen, as you can see. So the lower part is just for completing the model, and it's currently disabled. We have the fixed base. We have the three arms that are actuated by ideal motion drivers, the end effector and the connecting rods for the end effector. What I'm doing here is simulating the model. You can see that the inverse kinematic block already is on the canvas. So this model is pretty much finished. We'll have other examples as we go forward that might not be as complete as this one. So let's take a look at the animation first. So we are executing a command. We're going 1/3 of a full circle and then execute a pick and place. We'll come back and run this simulation again with the grippers as well. But let's go to the main topic of this example. So in MapleSim, as we will see over and over again in the remainder of this session, you will have additional information that you can include with your MapleSim model. And those are usually found under the attachments. In this case, under the attachment, we have a Maple worksheet for deltabot inverse kinematics. And we can open that by double clicking on that. So it will open Maple. And so here is basically a calculation sheet where I have typed in the equations and use Maple to solve them. So I'm just going to zoom in a little bit. Not going to spend too much time on the actual derivation here because this is pretty standard. You basically go from the center point of your end effector and write the full, basically the vector from this point to this point at the end of the arm, and we know the length of that that vector, and we calculate that length. So that will give us one equations for theta, which is our arm angle. So that's the equation that we need to solve to get the relationship between where our end effector is and the angle theta 1, theta 2, theta 3. So here is just a vector notation of the positions, and calculating the norm of that, and basically equating it to L2, which is that length. This is the constraint equation that we want to set to 0 and solve. Looking at it, we have the coefficient for cosine, coefficient for sine, and whatever remains that is not function of theta. So it's really becomes a cosine plus b sine plus a constant, and we can have Maple solve that. You have two solutions. We know which one we want to pick. So at this point, in this example, everything is done manually. I've seen the equations. I have the definition of A, B, and C. What I have done in this model is created a Medelica custom component. And I have the solution, as you just saw in that Maple worksheet, just put it here. And the definition for A, B, and C that I'm passing to this function that I've created. So the reason I've created this function is that, as you remember, we have solved it for one of the legs, and we just can use the same solution for all the legs. And then we put them all together in a Medelica custom component, generate that, and that becomes this component that we use to actuate the system. So this one is almost entirely manual, aside from the assist from Maple to solve that equation and give us in a very nice format so that we can use it. But we will see that for more complicated and more bigger systems, the manual approach might not be very convenient. So we will use Maple to generate the Medelica for us. Instead of, or at least parts of it, as we will see in the examples. So last thing on this example is just to complete it with giving it the grippers so that it will pick up the balls and put them on the ground. So it uses some other libraries in MapleSim, the multi-body library, and the pieces in there would be the grippers, the proximity sensor, and also the contact library. Okay, so that's our example number one, our first warm-up example. So we now go to our second warm-up example. I'm going to go back to the presentation and look at the example number two. The example number two is the very well-known Stewart platform. We even simplify that further to 3 degrees of freedom, basically confine the platform to translation only. The next example would be the full 6 degrees of freedom. It's just because we're going to dive into equations, this seemed like better suited for the purpose of this session. This one is also explicit approach, where the only difference really with the previous one is that in the previous one, we know how to drive the constraint equation. Here, we let Maple API to MapleSim to extract those equations from the model and then do the rest of the process using Maple to solve, and then putting them all together again in Maple and simulating. So let's go back to MapleSim, open the second example. It is, go up one, example number 2. I'm just going to open this. So here is the second example, also completed. So this is the expected configuration of the Stewart platform with 6 legs. We have some sample commands for how we want the platform to move. I'm just going to run this while I'll describe the model. If we go, the legs are identical. They are parameterized, so they all placed in the right location at the right angle, but the equation inside them or the configuration inside is identical. Each one includes its own inverse kinematic block that receives the demanded or required platform position as an input and calculates the length of the corresponding leg that gets actuated by, in this case, a ideal position driver, but this could be also a hydraulic system that gets its command from the inverse kinematics. Inside the leg, we have the a universal joint at the bottom to the ground, the prismatic in the middle, and the shoulder is a spherical joint. So there's a number of degrees of freedom here that form each of the legs. So here is the simulation of the system. The yellow ones are the universal joints, and the balls on top are the spherical joints. And due to the inverse kinematic that has already been implemented, the platform executes the commanded motion perfectly. So let's take a look at how this inverse kinematic is created. Similar to what we saw in the previous example, the inverse kinematic calculation worksheet is already attached. This is just a Maple worksheet. You can have Maple worksheets that do other types of work, analysis, pre-processing, post-processing. Here, obviously, we are concerned with worksheets that do inverse kinematic work for us. And there's a custom component that generated at the end under custom components. And that custom component is the equation for this block here. And we will come across a lot of these as we go forward. So just like before, I'm going to double click on this Maple worksheet to open it up. Here we try to go a little bit slower this time. The first command, this is an active session. This Maple worksheet is looking at the open MapleSim model. The first command establishes a link and creates a module A, and then we will use that module A to create the multi-body module, and that's where, as you're very well aware, multi-body has some very nice structures in it, and that can be utilized. So here's zoom out first to see all the system, the generalized coordinates, the generalized the first and second derivatives, or the velocity and acceleration coordinates, and the reactions to all the constraints in the system. It also reports that the system is modeled with 24 generalized coordinates and 18, so 6 remains, but we'll throw away another 3 so that we deal only with translation. So one thing that is first established here is that the leg equations are the same. What is happening here is that we get the position constraints for the system from the multi-body object, and the first 3 are for one leg, then the second 3 is for the next leg, and so on. So we'll just pick 2 of them. We use the same variables in both and subtract them from each other, the leg 1 constraints minus leg 2 constraints. And let Maple simplify the resulting expression, which is 0, 0, 0. So this is just a test to see that we can actually tackle one leg at a time. And here, what we are doing is creating looking at one of the legs in a more generalized way. So these are the constraint equations for one of the legs that has what we want, and some other variables that we might not necessarily need, but we need to solve for it to get to the extension of the legs, which is really this guy that we are after. But there are other variables that we need to solve for. So we can take a look at saying that for these three constraints that we get, what variable presents in which one, and how we can strategize a solving approach. So we can see that we can solve the second equation for alpha because it's only a function of the unknown alpha and the known platform position. So that can be solved directly. And then we can use alpha and beta. We can use the first equation to calculate beta, which we also don't need, but we need it for the third equation to solve for S. So that's exactly what we do. First solve for alpha, and then beta, and then solve for S. Now that we have the equations that we want, so together these equations represent the solution. We use the other API in Maple to MapleSim and have that generate the Modelica directly for us. And once that Modelica is generated, we'll just set it into the MapleSim model. This one was already there, so it says that you want to override, which is the same component that existed. And it will give us in our local components section the inverse kinematic. So this one was explicit, but almost entirely automated from the getting the equations. We did some checks and balances, but then we were off to a fast continuation with generating the equations that we want. We put it back and we were able to simulate the system as we wanted. So that's kind of concludes our second warm-up example, and we are at the halfway point. So I'm going to be, unfortunately, speeding up a little bit more, as I've already, this was a very quick review of these examples. So let's move on to our third example. And the third example is, again, a Stewart platform, but this is the first time we'll be looking at an inverse model. As I said, this is the most straightforward way of modeling. There's a little bit of a change in the model, the Stewart platform model, and for a good reason, because we're going to reuse the pieces back in MapleSim. So let's jump to MapleSim and see how this was done. So go back, file open, example number 3, open that up. So here we have the model here. We have a fixed base, and then we have the moving platform, and they're arranged as a Stewart platform is arranged. And what we are doing in the inverse kinematic block, if I go inside by double clicking, I'll see this. You'll see the same two pieces for the moving part and the fixed part, which are exactly used in the inverse model. And the difference is there is no real dynamics here. There is no degrees of freedom. We are grabbing the platform and rotating it and moving it according to our command inputs. So this is a prescribed translation, and this is a prescribed rotation. So 6 degrees of freedom. We are grabbing the end effector of our inverse kinematic inverse model and moving it. And instead of having the leg degrees of freedom, the universal joint, the spherical joint, the prismatic, all of that, we throw them out and replace them with a sensor, which basically measures the distance between the two ends of each leg. There is some offset that you need to apply if there is an offset between them, but basically this is your inverse kinematic solution. So this qualifies in, if you recall from the big table, this is an inverse model that is somewhat simplified. We could have left everything there, but this is a very easy simplification to throw out the legs and replace them with just a distance sensor. And they're brought to the boundary of the component, and that's our inverse kinematic. Just like the previous inverse kinematics block that you have seen, we just hook everything up together and simulate. And as we will see that there's really no difference between this block and the previous blocks in terms of usage in MapleSim, code generation, and other types of downstream applications. This represents a potential convenient approach to get to inverse kinematic for some difficult problems. And the last example that I have is a particular example of such case that the inverse model proves to be very, very useful. So as you can see, I can command the platform to do exactly what I want in 6 degrees of freedom. So compared to the previous example, when we go to Maple and generate the equations, had to do some checking and then finding out what equation includes what unknown variable, come up with a strategy of solving them, and then proceeding to solve them and putting together back into a component. This is a lot easier. But again, as we saw in that graph that I showed, that might be our starting point, but for certain cases, we might need to try to do something more efficient to hit our calculation budget when we are thinking about the application on PLCs or controllers that we want to put this on. So, but this is, as we have shown and used in applications with our customers, this is still a viable choice in a number of situations. And part of that comes from the core technologies of MapleSim and Maple, where we use symbolic math to create a very, very optimized set of equations for solving, whether being a nonlinear solve here or any other solution. So that's part of the reason we might be able to meet the computation budget even with an inverse model. So move on to my fourth example, where things potentially get a little bit more complicated. We look at our first large manipulator system. This is, as you will recognize from the setup, is inspired by some of the truck-mounted hydraulic articulated booms that are used in a variety of applications. So here we simplify the system to only a translation. There's nothing stopping us from having a 5 degree or 6 degree of freedom. 5 is more common in this type of applications to do the same. But because we're going to go into the equations and do some more advanced stuff, I felt like a 3 degree of freedom would be sufficient. So this one is implicit. Which means that we are going to generate the equations using Maple and MapleSim, but we will not attempt to solve them. So the process would involve building the model, generating symbolics, extracting, and then after the extractions, we won't be able to put them all in one command and generate the custom component. We actually need to put the pieces together and do some manipulation of the extracted Modelica pieces and then create the inverse block. And the rest obviously is the same as the previous examples. So let's see how that would look like. For this one, I think I've included multiple pieces. So let me just go to fourth folder, example number 4. So we have a start, finish, and detour. So let's start with start here. And this model that says articulated boom start is really not for simulation. This is our preparation for extracting the equations that we want. So the system is in place. All the degrees of freedom is in place. We have the rotating base. We have the first revolute joint for the first boom, and the hydraulic or the linear actuation in this case, and the second linear actuation, and the second piece of our articulated boom. As we have seen before, we'll just go to Maple where the magic happens. I will go through this again or step by step. So we'll have some familiarity with this. We already saw some of these. So first step would be to establish the connection. And the second step would be, we do a lot of stuff with multibody. So get that multibody module, which is very helpful in extracting a variety of different things that we will see shortly. This step could take a bit of time to put that together, that module. The good thing is that this is only in the generation part of our path to the inverse kinematic. We won't be doing this again after we have created the inverse kinematic block. So while that is happening, I can explain what the next step would be. The equations are generated in multibody with the system parameters left symbolic. In this case, we don't want to do that. We want to get rid of those parameters. So we ask Maple to, or the Maple to MapleSim API to get all the parameters of the system to us. And once that is done, okay, this is finished. It has 5 degree of freedom or 5 generalized coordinates. The system is 3 degree of freedom, so there's constraints involved, 2 of them. As I said, get the parameters so that we can substitute them away as we generating the pieces that we want. So one of the good things that we get from that multibody is the gate frame motion. Basically, we can find the vector to any point in our multibody in a symbolic form, symbolic parametric form in general. But in this case, we'll substitute away the parameters so that we will get the expression without any parameters. So that's the vector where the end effector is. And we also have a target for the end effector. And all we need to do is set them equal to each other. So right there, I have created 3 constraint equations, or 3 equations that I need to solve to find the the solution. And I can when I look at these equations, as you saw in the beginning, only interested in really theta 1. And if I go back here, I'm interested in theta 1 for R1 and S1 and S2. I'm not interested in theta 2, theta 3, theta 4, theta 5, and so on. So I'm not done yet. The work is not done, although I have created 3 equations. We have the position constraints that we come across in the previous one. So we'll grab those as well. Just like the previous one, we'll take a look at see what's inside. The position constraints are relationship between R3, R4, and R5. We'll add them to the list of equations that we want to solve. So we set them to 0 and add them to the pile as second batch of equations. So the first batch was the end effector equal to the target. The second batch would be the position constraint. And as I said, we are not interested in all the thetas. We're interested in the distances. So we calculate those separately or after the fact, because right now we have 5 equations already of 5 unknowns. So we can calculate R1, R2, R3, R4, R5. So based on R3, R4, and R5, we can calculate, and R1 and R2, we can calculate the lengths of the cylinders, which would be the actual value that will drive our controller or hydraulic system and what have you. So for that, we again go to get frame motion and say, give us a vector from the start to end of cylinder 1. Give us a vector from start to end of cylinder 2. And we'll just keep them as variables in the generated Modelica for the entire system. We put everything together in one list of equations and use the Maple to Modelica command to just convert that to a temporary Modelica. This is not done. We still have to massage that to make it ready. There could have been pieces that I can include here to do that, but I felt like it would be more straightforward to do that directly inside the editor. So if you go into folder, for example, number 4, you will see the generated equations. So this is what comes up out of that Maple to Modelica command. We have all the equations that we want. The constraint equations, the end effector equations, and the XYZ for the start to end of our cylinders. These are very large equations that we have the luxury of having Maple generate them for us, and we don't need to worry about that. So what I have done is that I do some mix and match, and let me just close these other ones that we'll get to hopefully. So I'll do some change of variables, add some additional pieces. So if you go back, you can see the inverse kinematic complete, which I have used Modelica, and I can actually, in my case, I have the coding, so this will be better. So I've added the inputs, outputs. I have the end effector as an input to my inverse kinematic. I have the ground motion as an input to my inverse kinematic. It could be on a boat, it could be on a truck, so that the base could move. And if we have those information, the inverse kinematic can compensate for. And at the end, although I have some other pieces that I don't want, but I have to calculate, the outputs that I assign to my inverse kinematic would be only the ones that I want, which is R1 theta, S1, and S2. And really the only additional calculation that I would add is that I convert those length vectors to actual, the displacement from end to end of a cylinder to an actual length of the cylinders. This code is grabbed and put in MapleSim. So the way I do that, let me go back, Control A, Control C, and I go back to MapleSim, go to code editor, and put a blank Modelica, paste it, and then generate the component for my MapleSim model. So that completes the inverse kinematic generation for my MapleSim model. We have the completed model, so I'm just going to switch to that. I encourage you to try to finish that yourself to get to this part. So now we have the commands, some path that I have provided, some disturbance of the base or the motion of the base, and I'm also tracking or plotting where the end effector is. I want to, excuse me, make sure the end effector is following the path that I want. So in this case, once the simulation is over, we can take a look at the system. You can see that these the cylinders are driven by the like an ideal position drivers. As I mentioned before, this could be a hydraulically actuated system using our hydraulics library, like the inverse kinematic and directional control valve and controllers are come together to actuate the system. We do have examples in that area. I'm not covering them in this session, but if you're interested in knowing more, do contact us and we can talk about those examples as well. So just simulating this for 10 seconds. Let's have a quick look at the results. So although the base is obviously moving, the end effector or the points of that V based on calculation are clearly only covering the commanded path. So this is a successful implementation of inverse kinematic for a articulated boom on a mobile system with moving base. So the complication that we can add here is, what if this system also, because it's big, so you can imagine, and depending on the application, if the application actually requires more stringent error tracking when the operator says move forward, up, left, down, or rotate, you want to have more accuracy. You might need to compensate for the effect of inevitable effect of gravity on the system. So and that's something that our approach of implicit equations and solving could also come to play there as well. So that's what I have for my next example. But before I go there, I almost forgot about the detour. So the detour is I'm not going to run this, but I'm just going to show it very quickly here. What I've done here, there is no inverse kinematic, but basically what I've done here is grab the end of the boom and move it. So this whole thing is the inverse kinematic for the system. You see that there is no actuation here, and I'm reading as I'm probing the three values that I'm interested in. So you can imagine this whole system can be put into a block and exported as a code where it receives the base displacement, the end effector desired position, and the output would be exactly what we want. So this is the starting point of a complete inverse approach to create an inverse model approach to inverse kinematics for this system. I thought that I include that to give you a perspective of one version with respect to another. So let me just close this and go back to our list of examples. So example number 5, there are more pieces here, obviously with the inverse kinematics. There are more pieces to look at. So let me start with the finish, then I will show you the pieces that needs to go together to make this happen. This looks similar to the previous example. I'm going to run that while I describe it. But just for the sake of simplicity, I've removed the base motion. There's really nothing prevents us from including those type of inputs here as well. So this is the same system as the previous one, except that for the last boom, the last segment of that, I've replaced the original, which was rigid, with one of our flexible beams from the multi-body library. And even I can include multiple the deflection modes. I've only included the vertical or the elastic coordinates for Z direction. The flexible beams in MapleSim use shape functions and as a solution to the partial differential equations that describe a flexible beam. So by including the number of terms, you control the accuracy. 2 is a very good guess for a lot of applications involving beams. And I've only included 2 terms, and there will be 2 additional variables associated with this formulation of a flexible beam. You might have a passive joint added to your system, which has linear stiffness and damping, and you want to include that as part of your lumped flexibility. The approach that is presented here can account for that as well. And the extra equations will be generated for the steady state deflection due to gravity, which will be thrown into the pile of implicit equations and solve all together for the solution to work as one unit. So here, let's take a look. Hopefully, the flexibility of the top beam will be visible in the demo. So this, I've actually included a very large mass at the end so that we can see the deflection. But even with the deflection, the IK is able to adjust the other degrees of freedom such that the end effector traces the exact path as commanded. There are dynamic effects that are not accounted for. And in a lot of cases, these type of manipulators are not moving that very fast. So this approach contributes to a much better accuracy of tracking and positioning for these type of manipulators, as you can see here. So these degrees of freedom are going to be different than what it was for the rigid case. To get to these set of equations, we actually have to create 2 models. I won't go to a lot of details for that. So we have 2 prep models that we need to put together. I've also included a rigid comparison so that you can compare what would a rigid version of this system would look like, how much extra joint motions are being applied from the IK to compensate for the flexibility, and so on. So part one of our preparation to generate the inverse kinematics is pretty much the same as what we have seen in the last one. Again, I have the Maple worksheet. I'm just going to have a quick look. But the difference between this one and the previous one is that when we do the steps, there is going to be two additional variables that we don't have any ways for solving, and those variables corresponds to the flexibility of the beam. I'm going to skip that because I'm running out of time. To get to those two equations, we use the part two of our prep work. So let me just open the part two. And this one is a bit different. As you can see, we thrown out all the linkages. We only kept the degrees of freedoms that correspond to the configuration of our robot, nothing else, or manipulator. And for the way we're generating the equations, we have removed the revolute joints and prismatic ones with motion drivers, so we can command the system to be exactly where we want. And we left obviously the flexible beam in place. So this one is very different. So we basically generate the equations for this system differently. Again, as before, let me see if I can run this. I'm just going to comment this out. As before, we established the link, but here we just go straight to the overall equations of the system with the get equations command to get all the ordinary differential equations of the system. And we get a list of variables that exist in these equations or the system. And we will see that those variables are going to be the flexure variables of our beam. And the next line here in equation 3, what happens here is that, let me zoom out a little bit now that we have the results. There's only two variables, the deflection variables for our beam. And we'll set everything, all derivatives to 0. So we get a steady state equations. And we can generate that to Modelica. I have included the two pieces generated in the folder as well. So let's have a quick look at those. So we have the two pieces, equation 1, which is very similar to what we have seen in the previous example, except that you will see that these equations are function of these variables as well. Actually, let's see if we can find them. There we are. So they are here, and we need to solve for them. And if we go to the second set that we are able to generate, we create two equations that are for these two additional variables. This is the steady state deflection under gravity. What we do, we'll put them all together. It's very similar to what we have done again in the previous example. And there we have the inputs and outputs. We combine all these equations together. So we have the balance the component with the right number of equation and not right number of unknowns, the same. And just like previous time, we calculate S1 and S2. And although we have some additional variables that we don't need, we calculate everything. Just like before, we put these all together in our component, a custom component, and generate the inverse kinematic block. So this is an extension of the implicit approach with the gravity compensation, and I felt like I should include that in this session because that's somewhat unique in a way we do that, and seamless in the approach compared to what the previous step was, to be able to use Maple and MapleSim to generate the equations, put them together, and then put back in the model. So there's very little time left. Thankfully, the last example does not involve any real work with MapleSim because I've already created an FMU for that. I mentioned at the beginning that in a lot of cases, the end goal is to be able to generate the inverse kinematic do a code generation on that, not just simulation. And so I'm just moving forward. The last one here. So this is again an inverse model, but instead of running it at the end in MapleSim, we're running that in MapleSim Insight, which allows us to run FMUs that are generated by MapleSim that have inside information embedded. So this is an inverse model. So as I will show very quickly, we have this complicated robotic system, and we want to find what each of these winches should command for this box in the middle to have 6 degrees of freedom. You can imagine writing the equation for this is quite a task, but the inverse approach makes really short work of this system. And really, we put a copy of the entire system back in the inverse kinematic, and we are able to code generate that and run it. And to kind of get a sense of the efficiency of that calculation, I have created shared with you an FMU of the entire system, not only the inverse kinematic part, but the robot itself. So on your side, you need to find the Insight application and run it, and then use the file open to open the FMU from the provided files. Once you do that, you get this view of the robotic system. This is the exported FMU from MapleSim, so it's already generated equations, optimized, and all of that are done. And we can go ahead and run the FMU. So if I run that one more time, you see that the pulleys are all oriented immediately at the start. Now we are ready to, because we have included some tunable parameters in this FMU, command the system to execute. And you can see that we are comfortably able to run this model in a real-time fashion. So we are commanding this to go at XYZ, and let's rotate this. This is in radians, so almost 90 degrees. We can go further than that. So this is an idea, kind of try to establish the fact that this approaches that we are talking about here, even the most expensive one, can be co-generated and be part of a real use case.